Yeah, welcome everyone for high performance computing, advanced scientific computing. Today we have our lecture 7 already. So basically you have already climbed kind of the midterm of the whole course. We switch a little bit the view on HPC, the topics on HPC, moving more from simulation sciences based topics with MPI and OpenMP to GPUs, deep learning, machine learning. This will be a, let's say, relatively high-level introduction. Usually for introduction to deep learning, you have something like I teach 3 days from morning till evening, introduction to deep learning, or basically a whole course in deep learning. Obviously, that's quite a substantial topic, and I will talk about why it's so successful these days, why it's so important today to know something about deep learning. But before we go into this material in this lecture today, let us, as usual, review what we had the last time. And we looked a little bit on the success of accelerators. So this is a name more generally speaking than GPUs. In the sense, it means something very similar. So GPUs are graphical processing units that accelerate certain parts of the application. In the future, we would have maybe other devices that also accelerate something. You would say quantum devices will come along where you accelerate some optimization on a quantum device, coming back to general purpose. Also, we have other ideas of chips in the future that are basically in one way or another always not getting rid of the general purpose computing that we have in CPUs and so on, but rather accelerate some parts of the applications, right? We, for instance, look also at neuromorphic devices right now as the next chips we would do as a module, basically complementing general purpose computing. That's why the idea of accelerator is a bit more broader. Also because GPUs were really shaped by NVIDIA. You hopefully learned that the last time. I think we could say around 95% perhaps of market share is GPUs from NVIDIA, from one vendor, based on the success of the last 10 years. But basically AMD, Intel, they're all catching up in this industry. So we will see in the future, like we have already now, the Lumi supercomputer, where Iceland is part of, has already actually AMD cards. So more and more supercomputers also adopt non-NVIDIA technology. However, the reality is also, if you look at the top 500 as it is now, here's a little bit an older version, but it doesn't matter. It still shows quite an impact that almost all the systems in one way or another, NVIDIA, yeah, so I can go on and go on. Today, to be one of the top leading supercomputers, it's always NVIDIA. Still, there's a world of change, and we see perhaps in the future more and more systems where we really see AMD, for instance, cards coming into the game. But for now, let's stay to understand this a little bit in the world of NVIDIA. One example I gave you was basically a couple of years ago, the #1 in Europe is our Jupyter system, still basically one of the best in Europe. And you see the amount of GPUs, which I also wanted to show you a little bit. So we have to go away in HPC from this little workstation client that has one GPU where it accelerates something. In HPC, we're talking a whole node with CPUs accelerated with GPUs, right? That means there would be always host CPUs. I hope that's what you learned the last time, right? So there's not a GPU operating on its own somewhere. There's always a host CPU needed that actually fuels the GPU with data, and so on. And here we just do it on a much different scale than just, having basically a little laptop and a small GPU inside. Here we talk about big nodes, and one of the architecture we put there was a Summit, another very huge American system. You have seen even 6 GPUs per node. We in Europe can afford just 4 GPUs per node. The Americans have lots of money, right? So they can afford 6 GPUs per node. And if you remember, I think it was in the order of 27,000 GPUs, while we have 4,000 roughly. So all is a bit bigger, as you know from US, but the key technology inside is still very similar because all of them are adopting NVIDIA technology. So they are NVLinks that actually also interconnect in these different nodes that we see here with 2 host CPUs hosting this 6 GPUs, right, as an accelerator. And still we have learned basically in order to fuel these systems, we always have to go via the host CPU, basically get there some data in, and then the kernel in that should be operating on the GPU parts, and then basically fuel the data into the device memory, as we call that, the GPU memory. And once basically the kernel is executed, on this kind of GPU device, the results have to come back to the CPU, back to general purpose programming, and then do something with the results, hopefully. So that's the modus operandi right now. As I said, lots of changes in the future where maybe some other vendors look on having a host CPU and a GPU at the same time. But in the moment, this is more or less how you program in parallel a GPU. Now, this lecture should basically be a little bit of follow on this, in the sense that this topic that I have for you today, deep learning, would be not possible without GPUs. Basically, we will learn this in some of the assignments from Reza, where we maybe also execute something on the CPU, and then you will see deep learning on a CPU doesn't make sense, right? It's very slow, very cumbersome, and the success of deep learning is really accredited not only to the interesting models they have now, but also mostly about the computing power. And this computing power is fueled by GPUs. That's why it's neatly built basically on that concept. Now, I'm also aware that many of you probably don't have used GPUs on deep learning yet. I know who has used deep learning models before. Okay, a couple at least. That's very good. So, but we will give a little bit an introduction basically here to artificial neural networks. Start very simple with the Perceptron. Needless to say that for a whole machine learning course, there are others here in the university, right, that we offer to understand this topic completely. Here we rather see it as an application topic and building basically a basis that then also Reza in his lectures can carry on, and where we build on this with different models. Today, we will therefore start very much, let's say, on the bottom, called the linear perceptron learning model. It's one developed in the 50s that actually mimics the neuron, more or less. And we will talk about this, and we will have an interesting data set about character recognition that we go through and extend then the modeling more and more to something we can call artificial neural networks. There's also something like multi-layer perceptrons, as they are called, and we will talk about this. And understanding with this the need for computing more and more by looking on the trainable parameters, right? By that, we also have to understand a bit by overfitting, which is more machine learning theory, but really the trainable parameter are now the part where the HPC comes in, why GPUs are so important. We will observe this already much growing when we just talk about machine learning, the first part. In the second part, we will move to deep learning with one concrete model that is called convolutional neural networks. They are actually for image recognition, while Reza will extend LSTM's GRUs on time series. So a complete different modeling, but carries the same essence of deep learning networks. So different models for different problems, essentially. Still, the idea is to go deep in the layers. That's what we will talk about then here, going from shallow learning with a maybe 2-layer artificial neural network here, up to a more deeper level. I have some nice visualization there also for this MNIST when we talk about these CNNs, how to understand them with feature maps, with weight sharing. And of course, again, the interesting idea with, again, looking at the trainable parameters, how they significantly grow as we go deeper in the network, but also then the complexity of hyperparameters, so picking different values really to understand what's the best network architecture is not at all clear. So there is also where HPC comes in. We not only train the model once and are done, we usually have to do it a couple of times to really find the best hyperparameters. And indeed, it could be leading up to 100 times just to find the best hyperparameters. And that's what we want to talk about. And of course, in the end, think about some limits, why basically these networks just achieve 99% and never 100%, like maybe more physics formulas could do. And this would be basically the key message. Again, the disclaimer, it's not a complete introduction to deep learning. We need a whole course for that. But essentially, you will learn a little bit about the idea of using now the accelerators for this deep learning, and also already for the artificial neural networks, so for the shallow learning models, that helps already there a lot. And then basically you have a couple of learning ideas of how you do parallel computing on a different level, because essentially the beautiful thing is in deep learning, you don't see it, right? You have a deep learning package like TensorFlow, like Keras, and the parallelization is done for you underneath. So even if you use 500 GPUs, it's automatically parallelized for you. And this is called distributed deep learning. We'll talk briefly about it with MPI or reduce and so on. But here you do parallel computing and still have a nice Python, let's say Jupyter notebook or Python, programming, which looks like serial, but inherently is parallelly executed. And today, these people, in the scientific domains, in engineering domains, use a lot of AI. So hence, this is also related to many of the things we do. And HPC programming paradigms is very clear. AI, GPUs, you have seen it's not only valuable for AI, also for Amber, for molecular dynamics, for other packages I have shown. Razor will extend to CFD. Everywhere, basically, accelerators have an impact, and also deep learning and AI models have also impacts today. So let's start with a simple introduction to artificial neural networks. We start here with a very specific focus on supervised learning. That means we have a certain data input and always know the guiding Y label. I give you an example later on. So we'd have basically a bunch of data set there with a certain dimension. And always when I know this data point, I know which class it is belonging to, right? So this is something which we call supervised learning because we have an annotation. There's also unsupervised learning where you wouldn't have that, used for instance in clustering or semi-supervised learning. But here what I will show is in the realm of supervised learning. It's by far the most understood. So let's look on some example. No. Does it change? Okay, now it's coming. Good, and here's one example of this. When you have the bunch of data points you have seen in the green area and you have seen it in the red area, one of these Ys, the guided basically fellow here, would be this class. So is it the green class or the red class? In this particular element of flower classification, it would be a particular type of the flower, Iris setosa or Iris virginica. Now, the idea of doing machine learning models is to find somehow a mathematical representation that would classify those. And you can see already, maybe someone in the room knows which flower that is. Is it Iris setosa or Iris virginica? Not so easy, yeah? So that's why we also do machine learning, automate the process. We look on some of the features inside the flower, the petal width, the petal length, to really automated find a way this must be an Iris virginica, or this must be an Iris setosa. So that's where we go basically for machine learning. We have some data items and we want to basically classify. Here's a binary classification, very simple, just 2 classes. Where we do research in remote sensing, we have maybe 52 classes to classify it, and using support vector machines and advanced materials like the deep learning networks you will see today. And how you model this would be, let's say in the binary, set up a line. Very simple. If you remember a bit basic linear algebra, you always basically have the idea how you would, put the kind of equation in the room, and then you would basically sum up the weights here linearly, and you would have some nonlinear activation function in it that basically then would be putting something through non-linearities later. But in the beginning, it could be a very simple function of saying -1 and +1 to basically classify the flowers. The red elements is now the interesting parts, if you think about this, because we don't know how to basically put the line in the root, because these are the constants, right? This is our data set. And we added here one bias for the orientation of the line, if you remember a bit on mass. And here's just a basically fancy representation is with X transpose W's. But the key message to take away is that the W's or the red parts in this are not known, right? In the moment, I don't know how to orient the line that basically would give rise to it. So this is the weights we're going to learn with machine learning, while of course X is our data set, it's a constant, right? This is our data set, we can always move through, go through, and do something with it. Hence, we have here a good example that you can follow now in the whole lecture to hopefully get to a, let's say, rough understanding of deep learning in this kind of 40 plus 40 minutes. And this is called the MNIST dataset. It has basically a character recognition problem with 10 classes. You can imagine from 0 to 9, all digits essentially, where they're handwritten examples. And we want to classify them automatically. Is this a 0? Is this a 1? Is this a 9? As everybody writes them differently, it's not so easy just comparing pixel by pixel all the time. So here we need some machine learning machinery that is looking at this 28 by 28 pixels. And then we'll say, well, that's a 0, that's a 9. And that's an 8. This data set is already nicely provided in Keras. So it's a machine learning toolset that we can use basically for us and nicely available. And of course, if you want to visualize them, they're looking a little bit like this. So they have this grayscale we would call, right? So it's a 0 up to 255 in times of the kind of values you have here in terms of intensity still basically grayscale, and every of these 28 by 28 would have a given label, right? Which would be here a 2, or basically here see a 5, a 0, and so on. Hence, this is a supervised learning scenario. For each of these images we have, which is here basically shown, I would have a guiding Y label that I can use for learning. What I do then traditionally in machine learning is usually I put something to the training set to build the model, and then I want to put it to the test set to understand if I really have learned. In the reality, it's not that simple. You would have validation data sets. In the machine learning course, you would also differentiate there a lot much more between these kind of elements. But here in this part of the course, it's quite enough to understand these parts of the problem. And so we have these digits, and now we have basically the tools, which would be Keras on the first place. But Keras is a high-level abstraction from another tool called TensorFlow. And the TensorFlow would have basically the support for GPUs and CPUs, right? So while reprogramming nicely Python scripts, basically looking all like serial, the kind of client that has done this will break it down into parallel computation on the CPU and GPU. And even if you then want to scale up to higher number of GPUs, we can scale this with Horowat and others. Just shortly, I think one participant has not muted. Maybe Lucas, I don't know, could you maybe mute? Thank you. If you want to play around with this, I would recommend the Google Collaboratory, for instance. This is an environment where you can quickly get also a GPU more or less for free. There's also a kind of $9.99 version per month where you can maybe have more access to this. Of course, when you have longer term project, we talked about the master, you can come to us here. In the university, we have also larger clusters, as you know, right? For GPU computing, for CPU computing. But if you want to play around, the Google Collaboratory is actually able to do the MNIST very quickly, for instance, here at home, and maybe for other projects if you want. But if you have a larger project, I would not recommend it, then please come to us rather. We can talk about access, also similar like you have basically already in the course. That's of course also something to realize. The same access would be also valid there. Right, to come and move a bit ahead, we have here some Python code, which nothing else is like in visualization that we have seen before. If you execute this one, you will see again this 28 by 28 pixels. So this is usually done before you do machine learning. You do data inspection, data visualization, data understanding to really understand the problem at hand before you do even machine learning, right? And now we basically get the confirmation almost like we have seen on the other slides, other parts or other slides where you have this 28 by 28 pixels with grayscale here for the different images guided by Y. And yeah, basically important is if you use it then on the Jupyter notebook or collaboratory environment, always think about the environment where you execute. This needs to be really connected to get then GPUs. Otherwise, you will see that it's not really working. The backends always must be connected no matter where you are. Basically, you see that also later in assignments, I guess, when Razor is executing this. That's important. Now, coming a little bit more now to back to the machine learning part, and we have seen this one equation where we have this, this kind of constants and then summed up linear using weights. Now we want to learn these weights, right? And now looking at this, we basically have a perceptron here, which is actually one-dimensional, right? So it's a bit of a problem. So we want to fuel this data, but we don't know how, because essentially we have a 2D input to this problem. This will be later in the key for deep learning in the second part of the lecture, to have a 2D input, but we have to break it down in one long vector to fill it essentially into a linear perceptron here. So that's what we can do. It's something called vectorization of problems. So we put the 2D input into a very, very long vector, right? Here and there, we normalize this a little bit. You have seen that's quite large numbers. And if you multiply them a lot, you quickly go out of the capacity of an integer or floats and so on. So that's why usually we do some normalization. That's why you see here 0 point something. These multiplied is actually still in the frame of references, basically in all the restrictions we have for all the different data types. But essentially, that's now important to fill it in the Perceptron learning model, right? I need a 1D input. And that's what I can do. The other thing we have to do is a little bit different than you have seen in the general Perceptron, was we have a multi-output Perceptron. So we would add not only one output, like the flower, you remember, Iris setosa, Iris virginica. Now we want to have a multi-output Perceptron using a softmax activation function of saying, this is a 0, this is a 1, this is an 8, this is a 9, right? So I have 10 different ways how to classify this image. And this now extending a little bit this normal Perceptron already to a multi-output Perceptron model, but that's not hindering us. More important for you is basically to know a little bit what that now means if you use this on the parameter perspective. So we have this long vector, which is 28 by 28 pixels times 10, which means we have 10 outputs to learn, because all of these needs to be a dense layer to learn. And there's always this one bias, right, that I was showing in the beginning. That's why there's a plus 10 for each of the different ones as a bias. So you come up to 7,850 weights to learn. So that's not a very big number. So hence here you're maybe lucky with a CPU can still do this. But now observe how these parameters will grow when we go now to neural networks, to deep learning networks, which is the idea of the course today, to really understand the computational footprint. In order to learn these, I have to go to the data many, many times and do something called optimization of the error. This alone would be perhaps a complete class to go completely into optimization. I hope some of you have heard from stochastic gradient descent before, maybe in other lectures. Stochastic, yeah, going downhill with the error. You have an error function you pick, like here is a categorical cross entropy. In this course, not for you so much important. It just shows us it's very usable for this problem at hand that we have with a 10 class optimization problem. And then to take the derivative of this, and you will basically go more and more downhill by always going minus basically the derivative with a certain learning rate, which is important because this steers a little bit the progress into this. How far you basically and how quickly you basically come to the next error part. And by this, you basically learn and update the weights. That's how it basically is working. That's why you will see there many times that the weights will keeping updating every time you take the derivative, the learning, and take it, and until a certain convergent. That could be, the converging could be happening at some fixed schedule. You say, we call that epochs. So after a certain time of epochs, it will be stopping. You see here number of epochs 20. It will just go, let's say 20 times through the whole data set in the kind of chunked down version of different batch sizes. So taking 128 and then learning from this how much basically we go to the error, taking the next. And there are some different ways how you can optimize. There's an Adam these days. So different optimizers that you can put in here. You see here SGD is just one optimization techniques. Adam is basically a very similar technique, but adding momentum. So the speed I already have going downhill and other elements into it. Also, this is not so important in this particular course to realize, but this is the computational heavy part where we now take the derivative, go downstairs, the error slope. And the more I have dimensions, this will be more added to the complexity. I'll show you an example in a moment. Also, what you see in the real source code that I was alluding to in the image before, you see we reshaped the training set, we reshape the test set. It's always what we needed to the idea of a very long vector, right? What we said we need, and then normalize a little bit here by the maximum value. And then we give here out the training and test samples. And then we continue with building the model, what you can easily do in Keras. And you see it's very easy, a sequential number of layers that I can add on with a number of classes in a dense connected network. So in the beginning, as the kind of figure was suggesting, we have, let's say, this 10 nodes, which are very, let's say, closely densely connected. So lots of weights to be learned. And the input shape, this is reshaped long vector we were talking about. So this is a very trivial, let's say, multi-output perceptron. We define here basically the model and then compile the model with a specific loss function or this error function, specify the Adam or the SGD optimizer, and then say what we get out there, the accuracy or so. So then we evaluate the model once we have trained it and fit it, as we call it, against basically our Y train, which is our labels, making it supervised, taking the batch sizes and going the number of epochs through this data set again and again and again and again, seeing how well we're doing, compute the error, and update the weights. And after 20 epochs, we have a certain weight status and can now compare the model how it would do on the test set, right? Which is then the second part. That's why we took the test set apart, taking it out of the corner and evaluate the model. And there is hopefully something coming out, which is a relatively good accuracy. You can play around this, and that's why I want to basically say a little bit of careful consideration here. If you do it too much, like 200 epochs, for instance, if you do too much learning, chances are that you overfit a lot, right? Because you learned so well, so to speak, that basically every little item is there. If you do just, let's say, one epoch, it would be probably not enough to learn. So you probably end up with underfitting. So finding the right number of epochs is already, so to speak, more or less a hyperparameter you have to search in the learning process how far I can go with learning. But if you do this, let's say, and basically iteratively learn from this, you see we come to kind of scores which are around 92%, which is already quite good. It's a very simple, trivial problem, but still 92%, if you think a human has to do all the work, if you automate the process, that's quite nice. You see still some instability. The SGD approach has some instabilities. Of course, it's not every time deterministic as an optimization algorithm, but you come essentially to a point that this model we talked about was around 7,400 trainable parameters that we now trained. So these red elements are filled with concrete values based on the learning process. We're reaching up to 91%. Nice. So what can we do to improve? Adding more layers, right? So now we have one layer, which was more or less kind of this perceptron in itself. So let's add two hidden layers, making it a neural network. And why we do this? Essentially, what you learned is to play around with a line. A line is not very strong, right? If you think about alone the XOR problem that I show here, it's not learnable with a line. You cannot find one line that is basically, putting a line that all the kind of values get correctly classified. There will be always one that is not correctly classified. The beauty of this multi-layer perceptron now, what we're talking about, is combining lines together to all sorts of shapes. The more, basically perceptrons you put, the more flexibility you have basically with the lines, coming to very nice decision boundaries we will talk about. So you see here what happens for this XOR if you combine it with two lines that you see basically here and here, you can actually come to a solution that XOR is solved, right? Only the space between these lines is considered this class and everything outside is considered another class. Just by combining this, what you see essentially here. So we're extending our idea of just having one perceptron, one neuron, connecting it to another neuron, what you see essentially here in the hidden layer. Right, so this is the first step in thinking how we do this. Instead of just going from the input to the perceptron and directly the output, we add a hidden layer neuron with it. So now I have basically two perceptrons in a way, but they are also connected to each other, which makes them even more stronger. And then you come to this kind of interesting idea. Still, it's very linear in shape, right? So we cannot do much about it because we have still lines. Now, the idea is now with the element I've showed you beginning, if you take one perceptron, which is this equation, all these signals going in, you come to something where we in the beginning said +1, -1, this flower, that flower, over a certain threshold, but you can put here a nonlinear activation function to catch non-linearities like this, right? Before we have been quite like this, right? The linear activation function, one line, we play around, we cannot catch maybe things where green and red is very interconnected with each other. But by acting then this non-linearities in the activation function, we can basically, by combining more and more perceptron, come to very interesting surfaces. Although I have to admit this example is a bit overfitted in practice, but you see basically it captures then the idea of having non-linear basically decision boundaries. And this is now what gives us some flexibility. There are different functions for this, like very popular is the ReLU or rectified linear unit these days. Very successful in many learning applications, but which one you really choose is also something we call a hyperparameter that you don't really know. In some occasions, some of these are actually much better than others. Something also to experiment with, meaning we have to do the experiment, the learning again and again with another, let's say, learning function, and again with another one, adding to more computing needs. Right? Still the same concept applies. Still we have per neuron, this one little neuron, the idea of learning the weights for it. But now as we combine them with, let's say, much more neurons in the hidden layer, and then we maybe even add another hidden layer, right? You can imagine now all these connections are weights which needs to be trained. So we massively grow the number of weights we have to train. And with this also the kind of computational footprint. We call this a multi-layer perceptron with a very specific way of doing back propagation of error. It's something invented to actually learn and train artificial neural networks. It becomes the so-called artificial neural network, basically a two-layer here that has a very specific way of being trained, because you have basically the guiding output Y here, but of course the neuron here cannot really access it because it has to move through all of that. That's where we talk about the learning algorithm, if you want, is back propagation of error using the chain rule of derivatives, and I cannot go in all the details here, but this is now the extension basically to the model we have before. And still we do the same thing with the optimization. Here's another view on this, taking the loss function. Essentially we go down an error slope, taking all the different, let's say, weights into account and using the learning rate. Now, if you do the learning rate, as I said earlier, a little bit too low or so, very slow, then you basically never go to the best minimum of error. Or if you take it too fast, then you kind of hop between the different, let's say, slopes back and forth, but also miss essentially the lowest error. So also finding the learning rate, and this is again the HPC part of it, is now a sensitive point, right? This is something nobody told you. It's again something you pick, and with this have to experiment on this. So taking different learning rates is something what we do in HPC automatically, doing hyperparameter optimization. And with this, having lots of HPC machine power invested in this, always GPUs, deep learning, doing the experiment again and again, but with different learning rates. So again, another optimization parameter if you want. In code, the same thing I basically talked to you if you want to play around with it. I can also make the source code available if you want, basically on Canvas. It has a similar options basically already that we talked about, epos, batch sizes, and so on. What's now interesting is, of course, we add more layers, right? This is what we said here before. We don't have the perceptron anymore. We have two hidden layers. So we have to specify how many neurons in the hidden layer. And also this is something nobody told you, right? So you can experiment, maybe 200, 500, 400. Again, new parameters, which basically you can choose from, and again, use hyperparameter optimization in HPC to really find the best values for your given problem. You see an activation function, which is now one of this non-linearity, this rectified linear unit I was talking about twice. So every time you basically see the signals coming in, summed up linearly, is not true anymore because I put a non-linear activation function in front of this, each time in each of the different neurons. Then the rest is almost the same. I have still a softmax doing the kind of probabilities between the different numbers. And if you train that again and again, you will come to something which is already very good, called 97%, right? So we went to 92, now we added several layers, 97%. The question is if there's some, better modeling still. So in a way, that's all what machine learning can do, right? So this is machine learning. It was not deep learning yet. We have a cutting edge artificial neural networks, 2 layers. Some people even say universal approximator to this. It can almost learn everything, but not to 100%. So this is already, let's say, a very good results for pure machine learning. What was the idea basically of part 1? You see also from the computing, we already have paid the price. Instead of, let's say, a couple of thousands, we have now 120,000 almost to learn in trainable parameters. And all of them have a computational footprint just for one model in one specific parameter configuration. If I want to change now the number of neurons from 100 to 200 in the hidden layer, another run. So every time I change some hyperparameter, I have to train again the whole network. So this multiplies with this number of parameters. Hence, over time, we can maybe, if you do now the 20 epochs yardstick to something which was 91 with the multi-output, and in the artificial neural network with the 2 hidden layers and 95% after 20 epochs. Now the question is, after the break, can we improve on this? Right, so I brought you here some also basically summarizing video that I will play over the break, but not here on the video. But we will continue then in 10 minutes with the second part, and we break here then to enter then deep learning afterwards.